2009 roads. So the map shows 5 metre vertical intervals. ABC is the central line of a proposed roadway. The section of the roadway between A and B is level at an altitude of 40. So A and B is at 40. This section from B to C has a gradient of 1 in 15 rising. Using slopes of 1 in 1 for cuttings and 1 in 1.5 for the embankments, complete the earthworks necessary to accommodate the roadway in its northern side. And the earthworks on this side here have been already completed. So I have cut and I have fill. I'm told it's 1 in 1 for the cuttings and 1 in 1.5 for the fill. So I have 5 metre intervals, so my ratio is going to be 5:5 and 5. 1 in 1.5 is fill, so it's 1 in 5:7.5. So the first thing I'm going to look at is I'm going to actually look at the road. So A to B is level, so it's at 40 meters altitude, and then B is constantly rising towards C at a rate of 1 in 15. So if I look here at the contours here, just as A to B, I have 50, 55, 60, 60, 55, 50, 45, and then here I have 40. So this contour here is actually 40. So that there is a point on the edge of my road. So I can see the earthworks beside the road here is higher than the level of the road, so I'm going to have to use cut. So my ratio is 1:1, so I have 5 metre intervals, so it's going to be 5 mil. So I'm going to measure out a series of 5 mils. So what I have there, I have 45, 50, 55, and 60. So that there is my 45 mil contour, 50, 55, 60, 60, 55, and 50. So I can draw in so that area there is cut. So the next thing I can look at then is my road between B and C, and I'm told that B to C has a gradient of 1 in 15 rising. So basically what that means, for every 15 that you walk along this road, the road rises up 1 metre. So for every, I can scale that up there, so for every 75 meters I walk up the road rises 5 meters. So if I measure off 75 here, I know then that the road has risen 5 meters, so this here is 45. If I measure another 75, I know that this point here is 50 meters. And I can measure another 75 here, and this point here is 55. So my road is rising here. So the next thing I'm going to do, I'm just going to look at the level of the road here, the contours around it. So I have 35, 35, 40, this contour is 35, 30, 25, 20, 20, 25, 30, 35, 35 and 40. So the road is higher than the earthworks, than the ground around the road, so I'm going to have to use fill, embankment. So I have a sloping road here, so the location of my cone, so if it's fill, I put the cone at the high end. So the first thing I'm going to work out is I'm going to locate my cone. I can locate my cone here. It's going to be here on the edge of my road. My fill is 1 is to 1.5, so that means it's 5 is to 7.5. So if I draw a radius here of 7.5, that will give me a contour 45. So I want to actually create a contour that will match up with this 40 mil contour here. So I'm going to, if I draw a radius of 15, that means that I will have dropped 10 meters, so that contour will be at 40. So I'm going to draw a circle of radius 15. And because that is radius 15, then I can join this then back to my 40 mil contour. So that there it is, 40. So the next thing I'm going to do then is I'm going to mark off a series of 7.5s along my road. So that will be 35 and 30. So I have 40, 35, 30, 25, 20. The first thing I can do anyways there, I have a 40 mil there, and that there's 40 there as well. This point here is also 40. And so is that point there. So that's 40, that's actually 35. So I have 35, 30, 25 and 20. That there is 45 and that there will be 50. So I can also draw my 45 mil contour here. And I can draw a 50 mm contour here as well. So once I have that done, then I can look here. So here's my 20 mm contour. It's 20 and 20. It's my 25. Here's my 30 mm contour. Here's my 35 mm contour here. And here. This here is also my 35 mm contour. 40 there. This here is 35. And this here is my 40 mm contour. This here is 30, which is here. 35, which is here. So I can draw in so I should have 40, 35, 35, so I have two 35s here. So that's my earthworks done there at that side road there. All that there is embankment. So the next part of the question then. On the map, D, E and F are outcrop points on the top surface of a stratum of ore. Determine the strike and dip of the stratum. So here I have a mountain. Inside the mountain I have a layer of coal, and as the coal breaks through the outer surface of the mountain, what I have is called the outcrop. So those 3 points there are on the outcrop. This here is called my stratum. So the first thing I'm going to do is I'm going to draw 3 points on my outcrop. So D to E and to F. So I want to determine the strike and dip of the stratum. Now the dip is the angle that the stratum makes against the horizontal plane. So what I'm going to do here is I'm going to project up these points to my elevation. I can see E is on 45, F is on 60, and D is on 35. So I'm going to just start off here. I'm going to draw a line here. That's going to be 35. And I'm going to mark off a series of 5s. So that's going to leave me with 35, 40, 45, 50, 55, 60, and 65, and 70. So I can see that D is on 35. That's my point there, D. F is on 60. So there is F. And E is on 45. So what I'm going to do, this is similar to the intersecting planes question. Determine the strike and dip of the stratum. So the strike is a true length along the surface of the lamina. So this here is a portion of a lamina. So what I'm going to do is I'm going to draw a level line in elevation. So this, the first thing I need to do, I need to get the edge view of this triangle DEF. So I'm going to draw a level line here in elevation, and I'm going to draw it out from E. Right level there on that. I'm going to project this point down as far. So here's my line. So that line there that I'm after drawing, that there is known as the strike. So if I have a level line in elevation, the strike will be my true length. So if I look along the strike, I will see the lamina as an edge. So I'm going to project along the lamina now, parallel. And I'm going to draw an X1, Y1. So to get my heights then, I'm going to take my heights. I can take my heights. So I know that D is 35, so I can measure up 35. I know E is up 45. I know that F is up 60. I'm going to measure up 60 here. So that there is D, E, and F. So that's that lamina as an edge, the edge view. So the dip is the angle it makes against the horizontal plane. So there's one way I can do that. I can extend on down this the edge view, project it on down, and continue on to X1, Y1. I will see the angle. Or I can copy this X1, Y1 line and bring it up here as far as D. And this angle here is the dip. That's the angle there. So a Askew borehole at D is drilled in a northerly direction and plan, and has an actual inclination of 45 degrees to the horizontal plane. It reveals the bottom surface of the stratum at a distance of 20 meters from D. Determine the thickness of the stratum. So what I have at the moment is I have one piece of information here to do with the stratum. I need another line here so I can see the thickness between the stratum. So I'm told a Askew borehole at D is drilled in a northerly direction and plan, and has a natural inclination of 45 degrees to the horizontal plane. So this here is my plan view. So what I'm going to do here now, this red line here, that there is the plan view of a borehole being drilled in plan in a north direction. So somewhere along that borehole I'm drilling down through. and it has an actual inclination of 45 degrees to the horizontal plane. It reveals the bottom surface of the stratum at a distance 20 meters from D. So looking at that view there now, there's very little information that I can obtain from that, because I'm looking down on top of it. What I need to do is I need to get a section view, so I need to draw an auxiliary. So I'm going to project off here 90 degrees. Draw an x1, y1. And I'm going to locate D here in this view here. And I know that D is up to 35. So this point here is D. So we're told it has an actual inclination of 45 degrees to the horizontal plane. So this here is my horizontal plane. So what I'm going to do is I'm going to create a line here at 45 degrees to the horizontal plane. So that angle there is 45 degrees. So it reveals the bottom surface of the stratum at a distance 20 mil from D. So this here is my borehole being drilled in this direction. So the bottom surface of the stratum, which is this bottom surface here, is going to be 20 mil away. So that there is 20 mil. So that point there that I'm after getting, I'm going to call this here X. That there is a point on the bottom surface of the stratum. So to determine the thickness of the stratum, the next thing I need to do is I need to transfer back this point back here to this view here. So I'm going to transfer back this X. That there is the plan of X there. Come back this way. And now I need to project this here up to this view here. So somewhere along that line I will have X. So what I'm going to do here is I'm going to take my height off my x1, y1. Here's my distance, and I'm going to mark it off here on this line here. That point there is X. So what you'll find with the stratum, that I have a head wall and foot wall, and both the head wall and foot wall will be parallel. So the next step I'm going to do then is I have the line here DEF. So this line here is going to be parallel. So that there is the thickness of the stratum. And what I'm going to do here then is I'm just going to note that by writing NT. That there is my question complete.